In this video, I wanted to talk about graphing linear inequalities when you have more than one variable. And we talked a lot about linear inequalities in one variable in chapter 1. And the gist of it, just to sort of recap, let's say we were looking at a simple linear equation like, I don't know, x is less than or equal to 2. When we were solving inequalities like that, we were trying to solve the inequality, get x by itself, get the answer. We could often graph the answer on a number line, which, we plot the dot and shade it a particular direction. But the idea of that graph was to visualize what numbers are solutions. There's a whole lot of solutions to this, right? Because, well, there's a lot of different numbers that are less than 2. 1, 0, -1, etc. -42, -1/2, whatever, Basically, the set of all numbers in between -infinity and 2 are all solutions to that inequality. And we use the bracket to denote that it's included, or a shaded dot, based on, either way is fine for writing that. So what happens when we add another variable? Well, just like with when we're talking about solving equations and when we're writing y equal 2x minus 4, it's very similar where when you add a second variable, there's a lot of different solutions. It's not just down to a single, it's kind of like the difference between x equal to and x is less than 2. X equal to is just a single point. It's a single answer to an equation. Whereas an inequality represents an entire region, shaded direction for lots and lots of answers. And so when we're thinking about linear inequalities, it can be helpful to start by thinking, well, what would the baseline equation look like? And then kind of compare and see, well, what would this, what's the difference between the equation and the inequality? Because if I said that y was less than or equal to 2x minus 4, y equal to x minus 4 is actually a part of this answer. And this inequality includes more than just the equation, because any solution to this equation would also be a solution to the inequality. But there would be a lot more solutions. Basically, any value which had a smaller y component than that would also be part of it. And so what I'm trying to do to begin with is talk about the basic idea of how an inequality differs from an equation, but also I want to teach you what are the step-by-step ways to do it. And we often refer to this as the boundary line for an inequality, and that's what step 1 always is to do. Step 1, graph the boundary line. It says if it is less than or greater than, use a dotted line. If it is less than or equal, greater than or equal, use a solid line. In this case, since we have less than or equal, basically we're going to graph the boundary line as a solid line. And this is pretty easy because it's in slope-intercept form. We can see the slope is 2, the y-intercept is -4, and that's all that I need to graph the line. And since that's step 1, let's go ahead and do that. And I'll try to talk about why we want to do all this as we're going. But basically, slope is 2, mean rise 2, run 1, and I can always just extend the slope like that to try to recreate what this line will look like. Or I could solve multiple points and plot them. However you want to graph the line is totally fine. We talked about a lot of different ways to do that back at the beginning of this chapter. Try to make that straighter. That's good enough. Okay. But basically, if we're trying to graph an equation, that's what we get in a line. Because there are a lot of different answers, since we don't know either y or x, there could be lots and lots of different ordered pairs that satisfy the equation. And the line represents all the solutions to the equation, which there are technically infinite of already. Now, for an inequality, there's going to be even more solutions, because not only can y be equal to 2x minus 4, it could also be less than or equal to 2x minus 4. And basically what's going to happen is kind of like over here, where x equal to represents a singular point on a one-dimensional line, like right there. And the inequality is everything, including that point, but also shading to the left. And it's very similar when we're switching to an inequality. And if you read step 2, it says shade the appropriate region, but basically you're going to take the line and you're going to shade in an entire part of the graph, either above or below the graph, depending on the direction of the inequality. And since it says y is less than or equal, this part is equal. And you can imagine if you had to guess, well, which part is less than, it's always going to be the part that's below. If you're looking at your graph from bottom to top, whatever part is below the line. And if I'm looking at this one, this part over here, you might say that that looks like it's more to the right, which is true, but it's sort of like glass half empty, glass half full type of thing, which, well, it's a perspective. Is it below or is it to the right? Well, technically it's both. But if we're looking at it, what I recommend is if you look at the y-intercept, which is at -4, it says that y is less than -4 if x was 0. And the place where y is less than -4 is downward, right? Because that's always less. Less is down if we're thinking in the y direction. And since y is less, that's why I want to think below, because y is in the up-down direction. But basically, we're going to shade in this entire region, and this shaded region represents our solution to the inequality. And now why? And mainly, another way you could think about this is basically every single point in the shaded area, there's a lot of points over here, basically every single one of these should be solved by the equation. By the inequality, I mean, because an inequality differs from an equation, but basically, why are all these points also solutions? And really, it's because of the boundary line. The boundary line dictates where y is equal to specifically those values. And every point below that line has a y value which is smaller than those sets of points, which is kind of the logic of why these will all work. But another way you could do it, which is an equally fine method for determining where to shade, is by what's called a test point method, where you could basically pick particular points on your graph, like this point, 0, 0, the origin is on one side of the line. I could pick another point over here, which is on the other side of the line, and I could test these within the original inequality to see which one works. And this is another way that a lot of people will teach you how to do this. So I wanted to just review that in here as well. But notice if I check the origin within the original inequality, what I would get is that 0 is less than or equal to 0 minus 4. And 0 is not smaller than -4, because negatives are always smaller than 0. So notice that if I check this point, that's not true, and it produces a false mathematical statement, which is why we'd say that this is not part of my answer, and that's why I don't shade over there. Now over here, but you could check any one of these points, which would take forever, but if I test this point, it looks like that's 1, 2, 3, 4, 5 to the left, so 5, 0. And if I plug that into my equation up here, I would get, well, y is 0 over there, x is 5. And again, I'm talking about this point right here. And if I plug in 5, 0, I would give me 0 is less than 10 minus 4, or 0 is less than or equal to 6. That's definitely true. 0 is smaller than any positive number. And what I can see is that point over there makes sense. And that's the idea of why we're shading this region, because you could check any one of these points. All of these will be solutions to the inequality. And basically these two steps are a way to help you remember how the process of figuring out where is going to be shaded, because the boundary line is always the edge. It's kind of like, well, why do we start with graphing 2? 2 is the edge of an inequality like this. This is the very maximum value that makes sense. And everything below it, to the left in this case, is going to be shaded. It's very similar here. Everything below the line in a vertical sense is going to be shaded in, because this line is the very boundary of what makes sense and what doesn't make sense. In the next video, I'll do a couple more examples and I'll speed it up a little bit, but in this one, I really wanted to take my time and talk about, well, why? What is the sense behind how we're answering this? And yeah, that's something that we often don't think about.